This is part 3 of my lecture on comparing standard deviations, where I'm going to talk about the two-sample test. The two-sample test is the variance ratio test, often just called the F-test. It's used to compare the variance, or equivalently the standard deviation, of two samples. And it tests whether the two samples could have come from populations with the same standard deviation. It's a parametric test, so the data, as usual, must be quantitative and normally distributed to use this test. We've got two samples to compare. Let's say sample 1 has got a number of measurements n1 and a standard deviation of ss1, and that sample 2 has a number of measurements n2 and a standard deviation ss2. Note that we don't need to know the mean of either of these samples, we're only testing their standard deviations. The appropriate test statistic is the variance ratio, F. F is defined as sp1 squared over sp2 squared. That is the population variance estimated from sample 1 divided by the population variance estimated from sample 2. Notice this is the ratio of the variances of the population, not of the samples. So we have to estimate the standard deviation of the populations from the samples by applying the Bessel correction. Remember, we apply the Bessel correction, the square root of n over n minus 1, to standard deviation. So here we're using variances, which are the square of the standard deviation. So the Bessel correction is just n1 over n1 minus 1 without the square root. So sp1 squared, our estimate of the variance of population 1, is ss1 squared, the variance of sample 1, multiplied by n1 over n minus 1, which is the Bessel correction. And also for sample 2, sp2 squared is ss2 squared times n2 over n2 minus 1. So how do we interpret this result? The F ratio is the population variance estimated from sample 1 divided by the population variance estimated from sample 2. So our null hypothesis is that these two variances are the same. So if both variances are the same, then the ratio is just 1. So F is 1 if our null hypothesis is true. So conventionally, we always put the larger of the two variances on the top of the equation. So by definition, F must be always greater than 1 or equal to 1. It can't be less than 1, because to have a value of F less than 1, we would have to have a smaller number on the top than the bottom, and by definition we always put the bigger number on top. That means that we can test our calculated value of F against the F distribution, where the expected value is going to be 1. Now the F distribution requires 2 degrees of freedom, one for the numerator, the top line, and one for the denominator, the bottom line in the equation. But in each case the number of degrees of freedom is the number in that sample minus 1. Note that this must always be a one-sided test. Since we said that F can only be bigger than 1, not less than 1, we only have one tail in the distribution to worry about. Let's do an example based on the IQ of lecturers and students. And if you remember, in a previous lecture we did a test to find out whether lecturers were more intelligent than their students, and we did a t-test there, assuming that both populations had the same standard deviation. And at the time we said, let's just assume that's the case. But now we have the means to test whether that was justified, because we know a way of comparing standard deviations. So our experimental hypothesis might be that lecturers and students have different standard deviations of their IQ, and the null hypothesis would be that lecturers and students have the same standard deviation of their IQ. The data that we had at the time was that the IQ of a sample of 4 lecturers was 110, 104, 114 and 120, and a sample of 5 of their students had IQs of 110, 107, 105, 113 and 100. remembering that this was purely hypothetical data that I'd invented for illustration purposes only. The data are clearly quantitative and should be approximately normally distributed, so we can use the f-test to calculate the ratio of the standard deviations to see if they are equal. So we previously calculated in lecture 5 that for the lecturers n was 4 and the mean of their IQs was 112, and we calculated a sample variance of 34.0. While for the students we had n equals 5 with a mean IQ of 107 and a sample variance of 19.6. Now we don't want the sample variance, we want an estimate of the population variance. So we have to apply the Bessel correction, which for variances is n over n minus 1, remembering that the Bessel correction for standard deviations is the square root of n over n minus 1. So since variances are standard deviations squared, the Bessel correction is just n over n minus 1 without the square root. So for lecturers, n over n minus 1 is 4 over 3. So we multiply the sample variance of 34.0 by 4 over 3, and that gives an estimated population variance of 45.3. We do the same thing for students. The Bessel correction is 5 over 4, so the estimated population variance is 19.6 multiplied by 5 over 4, which comes to 24.5. Notice that if you want to do this in Excel and you use Excel's functions var_p, that will give you the sample variances of 34.0 and 19.6. If you use Excel's function var without the p at the end, then it gives the estimate of the population variance 45.3 or 24.5. In other words, the var function automatically includes the Bessel correction. Back in lecture 5, we used this data for doing a t-test, and we used the Excel data analysis tool, which gave this output. Notice it gives the variance for the lecturers of 45.3 and the variance for the students of 24.5. Those numbers are already our estimates of the population variance, not the sample variance. So the Excel data analysis tool has automatically applied the Bessel correction already to these numbers. But whichever way you work it out, we've got the estimated population variances of 45.3 and 24.5, and we want to see whether those are equivalent. So for the F ratio test, we divide one by the other, remembering that we must always put the bigger one on top in the numerator. So it's 45.3 divided by 24.5, which is 1.8. We also need to know the number of degrees of freedom, both for the numerator and for the denominator. Now the denominator of 24.5, that's the number at the bottom of the ratio, came from the students, where n was 5. So n minus 1 is 4, and the degrees of freedom for the denominator is therefore 4. 45.3, which is on the top, the numerator, came from the lecturers group, where n was 4. So n minus 1 is 3, and the degrees of freedom for the numerator is 3. Therefore we've got an F of 1.8 with 4 degrees of freedom for the denominator and 3 degrees of freedom for the numerator. When we look at a table of the F distribution, we find that there's a different row in the table for each number of degrees of freedom in the denominator and degrees of freedom for the numerator. Remember, we had 4 degrees of freedom for the denominator and 3 for the numerator. Well, actually we see we've got 4 and 2 and 4 and 5, but not 4 and 3. So the value we want is somewhere between these two rows. We want a significance level of 5%, so we look up p equals 0.05, and we find that for our chosen number of degrees of freedom, it's somewhere between 6.9 and 6.3. Let's estimate that for 3 degrees of freedom in the numerator is going to be around about 6.7. So we've seen from the tables of the F distribution that for 4 degrees of freedom for the denominator, and 3 degrees of freedom for the numerator. Although it's not shown in the table, we can estimate from adjacent rows, and with a significance level of 0.05 we estimate a critical value of f of about 6.7. If you remember, our f was 1.8, so it's not reached significant level. It's not exceeded the critical value of f, so we can't reject the null hypothesis. Well, actually that's good news, because it means that we were quite justified in assuming that the standard deviation for both populations was equal. We don't have any evidence to say that they were not equal, so our use of the t-test with equal variances was perfectly justified. So that's the end of lecture 7 on comparing standard deviations.